Okay, picking up on 1.4, rates of change, tangents, and tangent lines and sensitivity, I want to make a comment about the last example we did, that the answer in the end means that the rock was traveling at 42.7 feet per second. That's the rock's velocity at 3.5 seconds. So just want to make that clear, that that's what we were finding. Okay, and if we had another A value, said we wanted to know at 2 seconds how fast was it going, we could plug in a 2 where we see the 3.5 here and here. Okay, all right, so now putting it all together, if I give you the function f of x is equal to x squared minus 3x, and if p is equal to p, the point in question that we want to find the tangent line at, 1 f of 1 is equal to 1 negative 2. We get that figured out here. So I want you to find the slope of the curve, y is equal to f of x at p, and then b, find an equation of the tangent line at p, and c, an equation of the normal line. Okay, so we'll pick up where what we want to do is we want to find for this, I've already got it started, where we take the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. And then all I did in the second step is I replaced f of 1 plus h with the function f of 1 plus h, x is out and 1 plus h is in, and then I replaced f of 1 with negative 2. So now we're going to work through this now, and so now I want to square the 1 plus h, so I'm going to be taking the limit as h approaches, let me make this a little bit bigger, h approaches 0, so it becomes 1 plus 2h plus h squared minus 3h, and then plus 2, and all of that is then over h. I've got these 1 minus 3 plus 2, so these cancel each other. And then we have a couple of h terms that we can combine, so we get the limit as h approaches 0 of h squared minus h, and then that would be over h. So this is equal to the limit as h approaches 0 of h times h minus 1 all over h. H's cancel, and then we have, this is the limit as h approaches 0 of h minus 1. So when we plug in 0, we get 0 minus 1, so we get the answer negative 1. All right, so we wanted to find the slope of the curve at p. So we found the slope of the curve at p. So there's our answer to A. A is negative 1. And then for B, we want to write the equation. So we already have the point. So we have y minus, I'm going to write the equation of the tangent line at p. So y minus a negative 2. Y plus 2 is equal to negative 1 times x minus 1. And so we get y is equal to negative x plus 1 minus 2, which turns out to be y is equal to negative x minus 1. Okay. All right, and then we have an equation of the normal line. Let me see if I can make some of this a little smaller. So then equation of the normal line for part C. For part C, we have y plus 2 is equal to, it'll just be a slope of 1 times x minus 1, the reciprocal. So it'll go through the same point, but, and we get y is equal to x minus 1 minus 2 should be x minus 3. And these two lines must be perpendicular with one another then. Okay, that's it for that one. Then I threw in a question just to kind of be a little bit from the past. The next one has to do with continuity and what's going on with this particular graph. So if we have y down below the exit question, then I added one more question after this. So find the points of discontinuity of the function. For each discontinuity, identify the type of discontinuity, removable, jump, infinite, or oscillating. So in this case, you can see that I've already factored it because they're polynomials. I'm thinking, well, what's going on? And you notice that the x minus 4's cancel. So that means there's a hole there at x minus, where x is equal to 4. So the restrictions, the domain, remember the domain on this function is x such that x cannot be 4 or 3. So at x is equal to 4, there's a hole in the graph, so we call that removable discontinuity. And at x is equal to 3, we have infinite. I was going to say, rather, change the order here. We have an asymptote. And then that would be our infinite discontinuity. Okay, so, and that's it for that one. So we have one more problem here. Read your text about sensitivity. See if you can glean a little more from this if you have any trouble. But sensitivity measures or describes how one variable responds to small changes in another variable. Okay, so if we look at this problem, maybe it'll clarify things. So sometimes we can understand better if we're going through an example. So a patient enters the hospital with a temperature of 102 degrees Fahrenheit and is given medicine to lower the temperature. As a function of the dosage, the measured in milligrams, the patient's temperature will be. So you're going to have to copy this down because I think I left it all off of your notes. So this is your function, T of D. Okay, I want you to find and interpret the sensitivity of the patient's temperature to the medicine dosage when D, the dosage, is 1 milligram. So sensitivity is when we take the change in the dosage, when the change in the dosage goes to 0, and it depends on what the dosage is. In this case, it's 1 milligram. But we want the change in dosage to go to 0. So again, it's that instantaneous rate of change, as if you'd be looking at your speedometer, 65 miles per hour. Okay, so what we're going to do is we're going to take the limit. So sensitivity is the limit as the change in dosage goes to 0 of delta T over delta D. We're going to say our A value, that particular critical location, is when D, the dosage, is 1 milligram. Okay, so we set up the limit as H goes to 0 of delta T over H. We're letting H equal that small change in the dosage. So we set up our functional notation so you can see what I'm doing. And since this is our function over here, T of D, we're first taking D and replacing it with 1 plus H, and they're going to take D and replace it with 1 for the second one. So the function is 99 plus 3 over 1 plus our input. So you can see that here we have a negative and a negative here, right? So the 99s are going to cancel here. So then if we simplify, this is equal to the limit as H approaches 0 of 3 over 2 plus H minus 3/2, and that's all over H. So recall that when we did limits and we had a complex fraction, we sometimes wanted to know how to solve this or how to simplify it. So what we're going to do is we're going to get a common denominator, and I'm going to skip that step. I'm just going to move right on to simplify it. But what I would normally do is bring the top to, maybe we better just do it. The limit as H goes to 0, so I'm going to bring the two terms together in the top by getting a common denominator. That means I need an H for the first term. And I have 3 over, I'm sorry, not an H, a 2. A 2 And I need a 2 plus h for the second term. That's still over h. Just simple. I think sometimes it pays off to go through things like this sometimes, rather than skipping steps. So we have the limit as h approaches 0 of, then what do we get? 6 minus 6, 6 minus 6 plus 3h, and that's all over 2 times 2 plus h. I'll just switch the order there. 2 times 2 plus h. Now you're dividing by h, which is the same thing as multiplying by 1 over h. Okay, so simplifying that a little bit further, then we have it's then equal to the limit as h approaches 0. So in the numerator we have 6 that becomes plus a minus, and so then we have 6 minus 6. Let's cancel those with green. Okay, so in the numerator we only have that negative 3h. And that's going to be over. I'm going to move this h over here. 2 plus h. There we go. So we're going to cancel the h's here. And that leaves us with then, we can go ahead and substitute in here because the h's just become 1s. So we get negative 3 in the numerator. And then in the denominator we have a 2 times the quantity 2 plus 0. Now remember, we have units on this original fraction. So if you're thinking about it, because in the bottom, what we have are milligrams. It's in dosages, right? And in the top, we have our degrees. That's our temperature, right? Change in temperature over the dosage. So it's degrees per milligram. So let's see what we get. So we get negative 3 force degrees per milligram. Okay, so this means that when the dosage is 1 milligram, a small additional dosage of a very tiny delta D milligrams will result in a drop in the patient's temperature of approximately 3/4 delta D degrees. Okay, so a drop of 3/4 degrees per milligram. Okay, that's our topic on sensitivity. So let me see if there's anything else. What I would probably do is take all the boxes from this section and go over the rules in here, and the slope at a point, and make sure that you understand this limit as h approaches 0 of f of a plus h minus f of a over h. But moreover, I guess I should say this, that let's split them up, that you have the slope of the secant line is just that f of a plus h minus f of a over h. And the only difference here is that when we find the slope of the tangent of a tangent line, we add that limit process to the whole mix, okay? And take the limit of the difference quotient, okay? So good luck on your homework, and I'll see you soon. Take care.